So, welcome to lecture series on advanced linear algebra. Friends, we have already seen for a linear operator defined over a finite dimensional space, that is for a square matrix considered over a field, we have seen the matrix defined over the suppose complex field, then it has eigenvalue and eigenvector. So, whether this concept, is it possible to say something similar concept for a rectangular matrix defined over the complex field or some field? That is the question. So, we know concept of eigenvalue, eigenvector for square matrix, but what can you say about the rectangular matrix? To answer these questions, today we will basically apply the concept of spectral theory to answer this question. So, let me consider an M cross N matrix over the complex number C. Okay. We have A star A is a square matrix, of order n cross n, because here A star is basically conjugate transpose of A. So, the notation I have used as a adjoint of A, but we have defined adjoint, basically it is we are limited in this course that adjoint basically mean for operator or square matrix. But here if I use the adjoint for rectangular matrix, this is I am talking only simply conjugate transpose of this matrix A. So, here A star is conjugate transpose of A. So, that is why if A is a M cross N matrix, where A is M cross N matrix, over C. So, now we see we have for any capital X belongs to C n cross 1, the set of all the column vectors defined over the complex number, then we see that X star A star A x, this is basically equal to something like Y star Y, where Y belongs to again C n cross 1. This implies this quantity is greater than equal to 0, this quantity is greater than equal to 0. So, this implies the matrix A star A is positive semi definite. If it is strictly greater than 0, I could say that this is positive definite. Anyhow, so here since I have picked up any randomly any matrix M cross N matrix over the field C, so I will say that this is a simply positive semi definite. So, if it is positive semi definite, then what can you say about the eigenvalues of this matrix? Now, what about eigenvalues of A star A? The questions. See, if lambda is an eigenvalue of A star A and Z belongs to say C n cross 1 is the corresponding eigenvector then A star A capital Z, okay, equal to lambda times Z, or Z transpose, I mean conjugate transpose, or I can say Z star A star A Z, okay, this will be equal to lambda times Z star Z. This implies left hand side LHS is greater than equal to 0 and RHS that Z star and in RHS Z star Z is also greater than equal to 0. I will say that strictly greater than 0 because Z is eigenvector, so it has to be non-zero vector. This implies lambda has to be either a positive real number or 0. So, eigenvalues of A star is either positive real number or 0. Now, based on this concept, let me write down one nice result, that is in terms of lemma like this. Let A be an M cross N matrix defined over the complex number C, then there exist unitary matrices U and V of order M and N respectively, such that A equal to U d V star, Okay. So, U and V are square matrices of order M and N respectively. A is M cross N matrix. So, to prove these results, I have to basically use the spectral theory. So, how we have to prove it? Let us see it. We have A star A. A star A is a square matrix and positive semi definite, or I can say non-negative positive semi definite. Also here A star A into A star A adjoint of that ones equal to A star A star A star A. You can quickly check that the matrix A star A is a normal matrix, that is A star A is normal. So, you can check it, this one I am asking you to do take it as a homework. that show that A star A is a normal matrix, is a normal matrix. So, by spectral theorems, A star A is diagonalizable with there exists an orthonormal order basis for Cn such that V star S star A into V equal to a diagonal matrix, equal to a diagonal matrix. Here V is a unitary matrix, whose columns are basically that orthonormal basis. I mean, we have already checked that if we consider normal matrix, then there exists a unitary matrix V such that V star into that normal matrix into V equal to diagonal matrix. So, this diagonal matrix is consist of eigenvalues in the diagonal. Okay. Here V star A star V will be equal to, I can say, diagonal matrix, since I have already shown eigenvalues of A star A is either positive real number or 0. So, if I consider there are exactly R number of non-zero eigenvalues, then I can write this is equal to say lambda 1 square, lambda 2 square and lambda r square and rest are 0. So, this is a n cross n matrix, where there are, we have assumed exactly r number of eigenvalues lambda 1 square, lambda 2 square, lambda r square, which are non-zero and rest are 0. It is also true that your this r is less than equal to minimum of m and n, I mean the order of the matrix, original matrix A. So, this results I have not proved that this number of non-zero eigenvalue has to satisfy these relations. This is a you can consider as a assignment problem. Consider AV. Since A is a m cross n matrix and V is a n cross n matrix, so AV will equal, which is basically m cross n matrix. Now, let me consider this is equal to the columns of the AV, like say let us consider x1, x2 and xn, where xj belongs to space of all m cross 1 column matrices over the complex number. So, if you see the star, according to this equation star, we have xi star into xj. If I consider, this is equal to lambda I square when I equal to j, for I equal to j equal to up to 1 to r, okay, 0 elsewhere. So, what I mean to say you, if I consider xi star into xj, because this is V star A star into AV. I have taken the AV equal to matrix consisting of the column x1, x2, xn, then AV star will be basically conjugate transfer this matrix only. So, this means that I am getting xi star into xj, I have to do multiplication like that. So, in this case I am getting, if I equal to j, then only I am getting this is lambda I square, but that is valid only up to I equal to j equal to 1 to r only, but after that, that is 0. So, this implies that after I equal to or j equal to r, I am getting xi star and xi equal to 0 for I equal to r plus 1 to n. So, this implies your AV, I am getting the actual AV equal to, it is x1, x2 up to xr 0, rest columns are 0 column only. So, this is the m cross n matrix like this, and the set x1, x2 up to xr is an orthogonal set of vectors in C m cross 1. This implies if I consider ui equal to xi by lambda I for I equal to 1 to r, if I do like that, then I am getting u1, u2, ur is an orthonormal set of vectors in C m cross 1. Since it is a orthonormal set of vectors, so definitely it will be linearly independent. So, therefore, I can use the extension theorems. So, using extension theorem, we can extend B into B star by adding m minus r more elements. B star equal to say u1, u2, ur and then ur plus 1 um is an orthonormal basis for C m cross 1. Now, let us rewrite. We have here AV which is equal to x1, x2, xr and 0 like this. So, this I can write down, this is equal to lambda 1 u1, lambda 2 u2 and lambda r ur, then 0 to 0 like this. Now, this can be also written equal to lambda 1 u1, lambda 2 u2, lambda r ur and 0 into ur plus 1 and 0 um. Okay. So, one can write like this thing. So, this implies AV equal to u into d, where u equal to the matrix consisting of u1, u2, um and d equal to diagonal of lambda 1, lambda 2 and lambda r, then 0 0 if m equal to n for m say greater than n. If it is m is greater than n, then d will be of the form of lambda 1 to lambda r 0 0, then again we will have 0 0. For m equal to n, the structure of D will be like this, and for m is strictly less than n. If m is strictly less than n, then D will be of the form of lambda 1 to lambda r 0 0, then again 0. So, D will be of this form. So, this is called spectral decomposition of the matrix A. Here we have AV equal to UD or A equal to UD V star, because V is unitary operator. So, inverse of it is basically the adjoint of it. So, A equal to this one. This is called spectral decomposition of the matrix A. Here lambda 1 to lambda r are called singular values of A. So, these are not eigenvalues of A, I am saying it is a singular values. This is a positive square root of the eigenvalues of A star A. So, now let me consider examples and let me show you how to construct the matrix U and V for a given matrix A. Okay, so let us consider an examples and show that how to find the singular value decomposition of the matrix A. So, here I have taken a 3 by 2 matrix over the defined over the complex field C. I want to have a corresponding singular value decompositions. So, in the very beginning I have to check what is A star A. Since A is a 3 by 2 3 cross 2 matrix, so A star A will be 2 cross 2 matrix, which is simply if we multiply A star A, it will give my like this what I have written here, that is 4 into 1, 1 minus I, 1 plus I and 2. Since it is a square matrix, we can immediately find out the corresponding eigenvalues, and we can see the eigenvalues of the matrix A star A are 12 and 0. So, let me represent this eigenvalues lambda 12 as a lambda 1 square and 0 as a lambda 2 square. So, we are looking basically interested for the singular values of the matrix A in terms of lambda 1 and lambda 2. So, corresponding eigenvectors we have can calculate, that is 1 and 1 plus I transpose, and for the eigenvector associated to eigenvalue 0 is 1 minus I and minus 1 transpose. So, these are also orthogonals, you can quickly check it, that is correct. This is simply dot product or your standard inner product over the C2, you can say it is equal to 0. So, immediately we can find out the corresponding orthonormal by dividing the norm of these two columns. So, I can write down the corresponding unitary matrix V, which is basically the consist of the orthonormal basis. The first element is eigenvector associated to 12, that is here 1 by root 3 into the column vector 1 and 1 plus I, and the second one is second eigenvectors. So, V star A star A V according to theorem is a diagonal matrix consisting 12 and 0. You can also cross check by simply multiplying these two matrices, that is V star A star and A V. Now, let me consider A V here, where here A V equal to I am getting here, I know V, so I know A, so A V will be equal to, I can calculate this again 3 by 2 matrix, which is simply root 3 times this matrix. According to our analysis theorems, your A V must be equal to, the first column of A V is the right hand side lambda 1 U1 and second one associated to 0. So, let me consider U1 is equal to x1 by lambda 1, x1 is basically first column of AV. So, here first column of AV is equal to root 3 times this column. So, this divided by the corresponding eigenvalues, square root of eigenvalues, that is lambda 1, lambda 1 equal to 2 into root 3. So, if I do it, then I am getting these ones. So, I have a E1 and other column is 0. So, according to theorem, I can form a basis for the corresponding space C3 cross 1 by adding 2 more linearly independent element that I have taken from the standard basis on the C3 cross 1, that is E2 and E3. What is E2? E2 is basically column 0 1 0, E3 is 0 0 1. So, I have E1, I have E2, I have E3. You can cross check this set of vector is a linearly independent. Fine. Now, I have to obtain the corresponding orthonormal basis for the space C3 cross 1. To get that ones, I have to use Gram-Schmidt orthogonal procedures. So, using that, let me construct my first linearly independent orthogonal element is x1, and x1 equal to I am saying that is u1. Okay. So, u1 is this one, fine. So, once x1 is calculated, x2 will be calculated by this formula using Gram-Schmidt, that is u2 minus inner product of e2 x1 divided by norm of x1 square multiplied x1s, which will give you this vector 1 by 4 minus 1 plus I 2 and minus 1 plus I the transpose. So, second orthogonal vector is also calculated. So, you can calculate x2 and similarly x3 will be calculated using same similar formula. X3 is equal to 1 by 2 minus 1 0 1 transpose. So, once x1 x2 x3 is known to us, then I can again make it orthonormal by dividing by the norm of the corresponding vectors, column vectors. So, that is I can have a unitary matrix U consist of the first column is x1 by norm of x1, second column is x2 by norm of x2 and third column is x3 by norm of x3, which is if you calculate it will give you value like this root 2 by 2 and this matrix. You see this matrix is a 3 by 3 square matrix, this is a 3 by 3 square matrix. So, then if I simplify, then I am getting U star AV, U star will be again 3 by 3 matrix into AV, A is my 3 by 2 matrix. So, U star A is basically a 3 cross 2 matrix and V is again 2 cross 2 matrix. So, it is basically finally 3 cross 2 matrix. So, I am getting that is a matrix of this structure, the first row is 2 root 3, that is the singular value of the matrix A or positive square root of the first eigenvalues of A star A, that is 2 root 3 and second row consists of 0 0 only and same to third row also 0 0. So, this is my corresponding diagonal matrix, this is a rectangular diagonal matrix please. So, in this way we have a singular value decomposition of the given matrix A. You can also do the same exercise for considering any matrix and do it, have feelings about this decomposition and see the beauty of a spectral theorem. I mean basically the importance of the normal operator or normal matrix. You can also see the applications of this spectral theorems for any other problems like to understand nature of the different form also one can use the concept of spectral theorems. That I will try to give a very brief information about that in my next class, which will be my last class in this course.